Okay, this is an optimization problem. We want to maximize the area right here enclosed by these fences. So we have a farmer with 2,000 feet of fence who wishes to build two identical rectangular enclosures like this. So what should the dimensions be of each enclosure in order to maximize the total area? So down here it says each enclosure will have a width, that's the short side right here. So talking about that distance of blank, and the length is the longer side right there of blank, and then we'll figure out the area. So it says each enclosure, so we're doing each one separately. Now this one, it does not have any variables defined for you, which means you get to decide what you want to call your variable and where you want to put it. I'm going to call this shortest side X right there. And the way you define it is just to put it on the diagram, and that way whoever's looking at your work and yourself will understand what the variable means. So if that is X, then I guess this side right here is also X. And we need to figure out what the length is in terms of X. Now that'll take a little bit of work. So the objective function, that's what we're trying to maximize, is the area. So the objective function is the area, total area. For now, I'm going to just call it y because I don't know what it is yet in terms of x. Now that's the thing that we're going to differentiate and find where it has a max, but we can't differentiate it yet because it has both x's and y's. So we need to get y in terms of x. And we'll do that using the constraint, which is what holds us back from just making the fence infinitely large, and that's the fact that there's only 2,000 feet of fence. So all these total fence lengths here have to be at most 2,000. So we have that distance x there, that's x, so that's also x, and that's also x. That piece of fence is y, and that's y. So we have 1, 2, 3, 4 pieces of fence of length x and 3 pieces of fence of length y. So 4x plus 3y is going to equal 2,000. So we are going to solve this. You could solve it for either x or y actually, but I'm going to go ahead and solve it for y since that's what I said I would do. So 3y equals 2,000 minus 4x, and dividing both sides by 3 gives us y equals 2,000 over 3 minus 4/3 x. And we're going to plug that in for y right there on a of x. So then area in terms of just x is x times y, which is x times 2,000 over 3 minus 4/3 x. Now you could go ahead and differentiate it at this point right here to try to find where it has a max, but I would recommend distributing the x first just to make it easier so you don't have to use the product rule. And then you find the critical values and solve from there. And now when you do this, let's just go ahead and do it. So distributing the x gives us 2,000 over 3 times x minus 4/3 x squared. I have not differentiated yet. Now I'm differentiating, so I'm going to call it a prime of x. The derivative of that is 2,000 thirds. And then of this, we'll bring the 2 down, times 4/3 gives us 8/3 x to the first. We'll set that equal to 0. Now that derivative exists everywhere, so there are no critical values that come from where the derivative is undefined. So we set it equal to 0. If we add 8/3 x to both sides and multiply both sides by 3, doing 2 steps in one here because I'm low on space, we'll get 2,000 equals 8x. So 2,000 divided by 8 is 250. So x is 250. Now that should be a max. I would check with the second derivative test real quickly, which is where we find the second derivative of a. A double prime, the derivative of the constant is 0, and of negative 8/3 x is negative 8/3, which is always negative for all values of x, which means it's concave down. The function a of x is concave down, so its shape is like that. So the critical value, where the derivative is 0, is right there. It is, in fact, a max by the second derivative test. Okay, so then you have X, and then what you can do is, it's 250 right there, is go figure out what Y is, that's the longer side, and then multiply the X and Y to get the area of each section.